All right, welcome everyone. What we're going to be doing today is we're going to be looking at some examples of working with data. Project 1 is out. You'll be working on that in lab this week. So I think it's a really fun project. I hope you enjoy it too. All right, so let's look at what we're going to do today. Today we're going to talk through some examples of looking at data sets using all these operations we've shown you. One of the themes of what we've been doing so far is that we show you some basic operations on data: select, where, join, group, pivot, and so on. And a lot of data analysis that you might be interested in doing can be done by piecing together those operations. These are operations that we didn't make up. You'll find this, for instance, in databases, the SQL language. You'll find this in folks who do large-scale data analysis like MapReduce and other places. So today we're going to look at some examples of working with these kind of operations and doing exploratory data analysis. When you get a new data set, how do you get a feeling for it? And then on Friday, we will start a new module. We'll begin starting to look at experiments and randomization and simulation and learning a little bit more Python coding to support analysis of that kind of stuff. All right, so this week you'll be working on project 1 this week and next week. You'll work on it in lab this week. I don't think we're going to have you work on it in lab next week. There's a checkpoint that's due this Friday, and then the rest of the project is due next Friday. We'll post slides after class. Somehow I thought I posted it, but I did something wrong in posting the slides. I'm sorry. But I don't have much in the way of slides today. Just brief review, and then I want to mostly do examples. All right, so reminder about pivot. We looked at pivot. Pivot is a method for cross-classifying. When you want to look at an association between two categorical variables, you can use either group or pivot. Pivot gives you a nice 2D grid. All right, so it's just a review of stuff we've seen before. All right, let's jump ahead. Join, we saw join. Join is a way when you've got data that's split across two tables to match up rows between the two tables and create a new table that has all the information in one place. Most of our operations work on one table. So once you get it all into one table, then you can use all the standard operations to do more sophisticated analysis. All right. So every row in the output table is obtained by matching up a row in the first table and a row in the second table. And the match is done based on the value of a column. They have a shared value in that column, then the rows are considered to match. Okay. Bunch of questions here. Maybe you want to ask detailed questions to Yanai, who's watching, and he can probably respond quicker than I can during lecture. Feel free to send me stuff, but I probably won't be able to answer all the questions in real time. Reminder of some operations we've seen. We've seen select for choosing some columns, take for choosing some rows, sort for ordering the rows of the table, where for selecting some of the rows that meet a condition, apply for modifying the data in a column using some function. We saw group. Group lets you combine rows based on the value in one column, in one attribute. Group can also allow you to do aggregation, where instead of counting the number in each group, you do some other kind of aggregation like the min or the max or the average. We saw a pivot, which lets you do cross-classification between two categorical variables. And we saw join, which I just talked about. Okay. If you want to ever get a reminder of all the operations or a brief summary of each one, we have a page on the course web page under resources. All right, so enough said about slides, and I don't want to do any more slides today. What I want to do today is I want to look through examples. I want to work with some data sets. So let me adjust my sharing. Switch over to the other window. Ta-da! Yay. Okay. Um, how's the font size? Big enough? Let me know if you want me to make it bigger. Where I'm going to start with is a very simple data set looking at billionaires around the world. Let's just read in this data set I downloaded. And it's got a list of a whole bunch of billionaires around the world as of several years ago, and their net worth and where they live and so on. And so maybe when you start to get this data set, it's got like 500 rows. So it's reasonable to want to get a feeling for what's in there and what kind of conclusion, what kind of questions might we be able to ask about this data set. So one place we could start is we could look at this location column. Where are these CEOs located? Which countries have a lot of billionaires? So we could do that by, well, let's see. A natural way to do that would be to group. By country. And this would show us a table that for each country shows how many billionaires there are in that country. So Australia has 7 and Brazil has 11 and so on. But it could be a little tedious to look at data in this numerical formula. So any ideas for what kind of a visualization might be appropriate to visualize this, get a sense for this? Nice, nice, nice. Lots of good answers. Lots of good answers. Okay, I saw some saying bar chart, some saying histogram, and some saying sort. So sorting is a reasonable idea. Sorting would be a reasonable idea. You could say, well, I'm really interested in a place with a lot of billionaires. So let's sort. Same kind of decreasing, descending. There we go. I can type. So you could say, let's look at the same kind of table, but put the countries of the most billionaires at the top. And there we see United States at the top. But that's not yet a visualization. So for visualization, yeah, a bar chart, a histogram, I like those answers. And actually, for this one, a bar chart is appropriate. Histogram is useful for numerical variables, but this is a categorical variable, so we should use a bar chart for that. So we can make a bar chart. Well, my typing today could use a little help, but there we go. We can get a visualization. It looks something like this. And we can see now from the lengths of the bars, maybe give us a better sense for just how common billionaires are. United States is an extraordinarily wealthy country. We are so privileged. And you can see how that shows up even at the very top end of the wealthiest. And China, Germany, and so on. Could also look at this by industry sector. We could kind of do this for each column in the table. We looked at, get a sense of citizenship. We could look at the industry sector. Like maybe it gives you some idea of if you want to become a billionaire, what sector maybe is your best chance, maybe. I don't know, it's a little hard to interpret, but we could look at doing the same operation and doing a bar chart by industry sector, and we get a different visualization. It looks something like this, and we can see, oh, there's a lot of tech billionaires out there. So no surprise that if you're asked to think of a billionaire, who might you come up with? I don't know. I tend to think of like maybe Bill Gates or Mark Zuckerberg. Maybe that's because I'm a techie, but there are a lot of them. Now, that said, you might be thinking at that, maybe this depends by country or by region. Like maybe in the US, we have a lot of tech companies, and so there are a lot of tech billionaires. But you could imagine maybe there are some other countries where they have a very large manufacturing sector, like, I don't know, maybe China or something. Maybe you might expect that the distribution in China would look different from the distribution in the US. So we could try to look at the relationship between the country and the industry sector. And one way to do that is to use pivot to create a 2D grid. And oh man, that's a massive grid. Doesn't fit on the screen vertically or horizontally. Industry, this column labeled industry, refers to the sector. So there's different sectors here, like commodity or consumer. And then there's industrial, which I don't know. I think that's probably manufacturing of some sort, but I'm not sure. So you can see this ends up being a table where we could get some information, I guess. We could see here what the distribution is in China. There's 6 billionaires in the consumer area, 5 in food and beverage and so on. But it's a little hard to interpret all these numbers, right? So that's a lot. That's a lot of data. And you might want to summarize that and say, so many rows here. I just can't, it's too much. All right, so what could we do about that? Maybe one approach we could do is we could cluster these countries by geographical region, by continent, for instance, okay? So how do we do that? Well, I downloaded and grabbed a data set that has a mapping between all the countries in the world and which continent they're part of, okay? So now I've got one data set with the billionaires and another data set with the countries. And I'd really like to associate each billionaire with a continent so that then I could do this clustering, this grouping by continent instead of by country. So how am I going to do that? Well, now I've got data that's split across 2 tables. So a join. Join. And we want to join by country. Both of these tables have a country column. We have a country column for each billionaire, and then this table has a country column. And so we kind of like to, for each billionaire, look up a corresponding row in this table based on what country the billionaire is, and then figure out the continent, and then add that continent column to the table. And that's exactly what the join operation does. All right. All right, so let's go ahead and do that join. And if we do a join, then we get a new table here. You can see it's the list of all these billionaires. Well, now it showed up in a slightly different order, but the same list of billionaires, the same columns from the billionaires table, but one new column, the continent, which was taken from this second table. And the way it was taken was by doing this matching, matching up the citizenship column of the billionaires table with the country column of the countries table, and finding rows that have a match. The citizenship, the billionaire citizenship matches the country in the countries table. Okay, so now we've got, with each billionaire, we know what continent they're a part of. All right, so now we can do this visualization or this pivot table we were looking to do, where we can break things down by continent instead of by country. All right. We could relabel citizenship to country, absolutely. But yeah, that's fine. It doesn't really help, because what we were looking to was to get to the billionaires table some additional data, the continent, right? So let me just remind you what was in the billionaires table. The billionaires table was country, citizenship, but not continent. I wanted to get one more column in here with a continent, so that then I could group by that or clump them together by that. So that's what the joining helped me do. If we look at the new table, and I apologize for all the scrolling and making you dizzy, but here's the new table. It's basically the same, but we added one more column, the continent. All right. Why is the column labeled continent after the join? Well, where did this continent column come from? We joined it with this second table, and that join picked up every other column of this second table. What were the other columns? Well, in this case, there was only one other column, the continent, and they got added. If this had had 7 columns, then the other 6 columns other than country would have all been added over here. Why is the order changed? I don't know. It's just the join doesn't promise to preserve the order. No particular reason. Where did the country column go? Well, the join removes the country column. Not sure I have a really good justification for why. That would be a reasonable thing to do, but it's what our join operation does. Where did continent come from? Continent came from this second table. See, the second table we got here had a continent column, and that got copied onto the billionaires table. But the copying was done in this appropriate way that matched up from the country, the citizenship, in the billionaires table, map that to the continent using this second table. Okay. All right, so now we can remake this pivot table, but we can do it at this point grouping by continent instead of by country. And now you can see some numbers here. So maybe it's a little bit, now you have a little bit more reasonable sized data that you could look through and try to decide, what's the variation. Like manufacturing, we see a lot of that in Asia and Europe, I guess, in this industrial sector. Media and telecom, we see a lot of that in North America and so forth for billionaires. Okay, so that's billionaires. One of the, we kind of got curious about, this, folks who are very rich. I wonder what kind of effect they're having on the political process and what kind of donations they make. So we found a data set from 2016. It was not billionaires, but this one was CEOs, many of whom were very wealthy, and their political donations. So let's take a look at that data set. Here we have got a list of CEOs and the company they're CEO of, and political donations they made. I think this is between around 1990 to, or maybe about 2000 to about 2016. And the party column is coded in this funny way where party 100 means it was donated to Democrats, and 200 is this amount was donated to Republicans. So party is categorical. It would be clear if this said Democrat or Republican, but this is how the data set came that we downloaded. So you work with what you're given. All right. Now, so over 4,000 CEOs in this data set. Hard to, not going to scroll through and look at all 4,000 rows in that spreadsheet. So typically want to start with some exploratory data analysis, get a feeling for what's there in the data set, and maybe that will drive some interesting questions or lead you to dig a little deeper. The amount, I forget what the amount is. That's a great question. I might be dollars. Oh yeah. Someone pointed out a really good point here. Look at this first row, Bob Ulrich. Look at this third row, Robert Ulrich, CEO of 3M. What's going on there? This is something that happens a lot when you work with real world data. I don't know, my guess would be they filed out the paperwork for one donation he made and he filled out his name as Bob Ulrich. And then most of the other donations, he filled out the paperwork. They had to report the donations as Robert Ulrich. So same guy, CEO, same company, just happened to enter in his name differently on one of the forms. And so it showed up in this data set under a different name. But you and I know that's not actually a different name. That's the same person. So this is really common when working with real world data sets, that the data is a little bit messy. Often one of the first things you have to do when you get a new data set is do some cleaning. Like really probably what we ought to do is we ought to combine Bob Ulrich and Robert Ulrich, combine those two lines so that to know that the total amount was not 591,000, was 599 or 560,000. All right, we didn't do that in this example, but in real analysis, often it's very common you have to spend a bunch of effort doing that tedious data cleaning task. A lot of the data sets we will give you in this class, we've actually cleaned them for you, so you don't have to deal with that, to spare you from that. But if you go out into industry, this is definitely a part of the data analysis process. Charles Rosati appears twice. Oh, that is a great observation. Charles Rosati, why does that one appear twice? Any ideas why Charles Rosati appears twice? This is a different issue. If you notice, the party is different. So Charles has donated to both Democrats and Republicans. So it shows up twice. How would I clean the data? There's no really systematic way to do it. In this case, I'd go look at what are the issues, like, oh, someone's name was maybe misspelled, or they used a nickname, and then I would have to go in some ad hoc way to go correct that. Like I might run through a spelling checker and find all the rows with spelling errors and go look at them by hand and see if they need to be corrected. I might try to split these based on first, last name, look for rows where it has the same last name but not the same first name, and eyeball that and see if it looks like there's some there where it's probably the same person. You know, there's a bunch of ad hoc things you could do to be very specific to each data set. That's one reason we don't teach it to you, is because it's not rocket science, but also, you know, it's very specific on the particular data set. Okay, so we can make a histogram of the amount they donated. That's probably one of the most interesting things in this table, is how much do they donate? And this has got to be the most stupid, boring histogram ever in the history of histograms. Look at that, everything's in one bar. What's going on there? Well, I'll tell you what's going on. What's going on is that there's someone over here, there's some outlier who's donated a lot. So let's check that out. Here we have, I've sorted them, the CEOs, by the amount they've donated. All right, so here you can see number one. Does anyone recognize who that top person is who's donated the most? Can I zoom out just a little? Let's figure out how to do that. Yeah. Yeah, you might know her by the name Meg Whitman. She ran for governor. She was actually a candidate, and she donated, I guess, maybe $125 million of her own money to her campaign. She was a Republican candidate for governor. All right, so that's why. John Huntsman, also political candidate, if I remember right. And then you'll notice here Sheldon Adelson and Sheldon G. Adelson. Oops, we should have done some data cleaning. That's actually the same individual. Those probably should be combined. The total donation there is more like 11 million than 6 million. Yeah, this is very interesting. Yeah. Someone points out these top donations are all to Republicans. Lots of interesting things you can see in this data set. All right. Who's made the smallest amount? There's someone who donated $9. All right. So maybe what would be more sensible would be to look at histogram, just the ones who have a modest amount of donations, but not, you know, Meg Whitman, not these outliers like Meg Whitman. And then the histogram won't all be just one bar. And then you can start to see more. And you can see that overwhelmingly most of the donations are fairly small, and there's a small number who make a huge amount of donations. So if you were looking for donations at a political party, you might say, oh, wow, you know, a handful of people make a huge donation, they might make a big difference. Now, what about that billionaires data set? Well, we could match them up. We could combine, look for folks who are both billionaires and CEOs, and then look at what kind of donations they make. So we do that with a join. Okay, so we could join them, match up the name of the billionaire with this the similar column. It was labeled CEO in the CEO's data set, and look for all matches. And if we do that, then we get the following table here. For instance, Barry Diller is both a billionaire and a CEO. So you can find here from the billionaires data set, it shows his net worth. And from the CEO's data set, it shows what company he's a CEO of. And it also shows the amount he's donated. He's donated 100,000? I don't actually know the units. I don't know if that's 100,000 or if that's 100 million. Not sure. So we could then start to scatter plot that. Maybe it's interesting now that we have for each one of these individuals their net worth and the amount they've donated. Maybe it's interesting to look and see, is there a relationship between their net worth and the amount they've donated? I don't know. Maybe it's not clear whether there's an association there. And you could start doing a whole lot of additional analysis, like, I don't know. what fraction of their net worth have they donated to political candidates. And then we can see this in this contribution percentage and normalize their contribution by their net worth. And you can see an awful lot of them are donating what would be a tiny, tiny fraction if each of us donated that fraction of our net worth. Okay, so that was just an example. You could go a lot deeper on all of this. And I kind of want to leave it there. I'm not a super expert on this topic of political donations, so you'd want to talk to someone who studies that to go deeper into this. How do you show a different color for Republicans and Democrats in the histogram? Ooh, 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 ooh. I love that. That is awesome. Let's do that. Oh, we got to do that. We totally got to do that. That is such a good idea. Wow. I didn't prepare this. I hope it doesn't go off the rails. All right, let's first get a table of all the, let's see how we're going to do that. Yeah, let's get a table of all the CEOs' donations to, yeah, to the Democratic Party. All right, we can do that. We can do that. CEOs.where, and then that table had a party column. All right, so party. Check and see if this did what I wanted. No. Oh, what was that? What is that equal to? There we go. All right, sweet. There's the Democratic CEOs and the Republican CEOs. And I don't actually mean Democratic CEOs. I mean CEOs' donations to the Democratic Party. So now let's get the CEOs' donations to the Republican Party. Look at that, make sure that looks reasonable. No, not reasonable. Republicans is 200. Huh. Oh man, I hope this doesn't go awry. I did not prepare this. I'm trying to do this on the fly. Okay, good. That looks reasonable. And now I suggest we can do some histograms. All right. Love it. This is so good. All right, I'm going to make two histograms. And then we can kind of zoom a little bit and see if we can get them both on the same screen. There we go. All right. On the top, donations to Democrats. On the bottom, donations to Republicans. So those histograms don't look that different when we exclude the very, very large donations. That's interesting. Maybe the ones to Democrats are a little bit smaller. I don't know. Hard to say. Could you put them in the same histogram? I think there's a way to do an overlay, but I don't want to try to do it on the fly because I'll probably get it wrong. So why don't you ask that one on Piazza, and then we can take like 3 minutes to test it and make sure it actually comes out right. I don't want to do that one on the fly. Yanai suggests this. Yeah, Yanai's faster than me. Let's try that. Is this going to work? Oh, sweet. Oh, that's right. Yeah, the group argument. That's just what I needed. All right, there you get two histograms. And they're kind of each transparent, so you can maybe see where the overlap is. If I zoom back in now, you can see here, you can see the overlap is here, and this is a part that's only yellow. Okay, so that would let you compare the shape of these two, and the shape are maybe not that different. All right, let's move on. I want to move on to new data set. There's various stuff you can see in this notebook. You can see an example of meteorites, but I want to do a new one. I want to look at a data set from bicycle trips in the Bay Area, which I think is really neat. So there's a bike sharing system where people could rent a bike from any of a number of locations, like BART stations and so on, for a short bike trip. Pick up, unlock the bike from the bike rack, hop on, go bike to wherever they're going, drop it off in another location. This is especially intended for like commuters, like you take the BART and then to BART station and then hop on this bike to your maybe your workplace or someplace else. And it was free for trips under 30 minutes, I think, for commuters. And this organization that was doing this bike sharing service publicly released their data set. They said, hey, help us go analyze the data and see what can we learn from this experiment we did with this bike sharing system. So they kind of crowdsourced the data analysis. Lots of people took a look at it and analyzed it. We could do that too. All right, so now this is a very large data set. It's like 40 megabytes of data. And so if you try to run it on our servers, you may or may not succeed. You might crash the server because it takes a lot of memory. You can see here there's 350,000 rows in this table. So what is this table? This table is a table of bike trips. So there's a recorded, each row represents one trip where someone checked out a bicycle from some location. That's the start station. Tells you the time, where and when they checked it out. And then it tells you where they returned it and when. All right. You can also, let's see, what else can you see? You can see the duration of the trip, how long between when they checked it out and when they returned it in seconds. Okay. Anonymized, no individual names there, but we can see all these trips around the Bay Area. So pretty cool. Now, if I wanted to start looking at this, one of the first things that jumps to my mind to look at, get a feeling for this data set, just to start, would be to look at how long are different bike trips. So let's do that. Let's make a histogram of the duration. And there it is. Yet another disappointing histogram. Yet again, one of the most boring histograms ever. So what's going on here? Let's understand what's going on. Let's take a look. I think what we're going to discover is there was a bike trip that had a duration that was like way the heck out here, but it was just like one out of like how many? 350,000 bike trips. And so the height of the bar is really, really small, so small you can't even see it on the screen. All right, so let's take a look at, well, of course that doesn't work because that's not the name of the table. Sort. Sweet, there we go. Okay, so I'm gonna just sort all these trips. Same table, but now sorted by duration, and take a look at those longest trips. And here, whoa, dude, look at that. The duration of that trip was 117 million seconds. 17 million seconds. How much is that? Let's see. 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. Let's go there. Let's go with that. 200 days. That was a 200-day long bicycle trip. All right, so did someone, oh yeah, I could look at the start date and the end date. Oh, I made my life so much harder. December 2014, return in June 2015. So what's going on there? Did someone borrow the bike and the bicycle like across the country and back again or something for over 6 months? No, that bike was stolen. It was finally found. So that's not a real trip. This is not what we want to understand. And, there's a couple other like this. So this happens in a real data set when you've got 300,000 entries. Weird stuff happens, and you get these rare cases like this. Sometimes they're called outliers. You could also have data entry errors. If someone's entering in some data and they type in the wrong year, you could easily end up with a trip that looks like it takes a year and 5 minutes instead of 5 minutes. So that's another source of these. So there's various reasons why this can happen. Let's focus in, maybe not look at these outliers, because they're maybe not, that's not that interesting. That's not really what we're interested in. Maybe we could focus on these free trips. So it was free for under a half an hour, because that's mostly what the intended use was for this kind of last mile for commuters. Okay. So we can do that. We can look at only the trips that take less than 30 minutes. That's 1,800 seconds. And we can draw a histogram of the duration of those trips. We can look only at those trips. And now we see, oh, okay, now here's a histogram where I can see something interesting. You can see that a lot of the trips are taken somewhere around, I don't know, let's say 200, 300, 400, 500, 600, 700, 800 seconds. So what is that in human terms? 600 seconds would be 10 minutes. 300 seconds would be 5 minutes. So you can see these are mostly very short trips, 5 minutes, 10-minute trips. These are people who are getting really close with the BART and then are just doing the last mile on the bike. Get to work, maybe. Who knows? All right. And I can control the width of the bins. In this case, there's a lot of data. So if I wanted more granular information on the shape of this, I could choose narrower bins. I could say I want 60 bins. And now I can see this shape here. You probably wouldn't want to do this if you didn't have a lot of data, because there'd be a little bit of noise in the height of each bar, and the fewer the number of observations there are in each bar, the more noisy each bar is, and so you probably want to use fewer bars. But for this data set, you could. So let's look at how to interpret this histogram. Here's a little quiz for you for how to interpret histograms. This would be totally the kind of question that we often have on like a midterm. Looking at this histogram, how could I tell how many people make a trip that's between 250 to 500 seconds long? How many of these trips involve, maybe what fraction is a better question to ask. What fraction of these trips are from 250 to 500 seconds? Good, yeah. The area of the bar should be that fraction. Great. And what's the area of the bar? The area of the bar is the width times the height. So we just got to find the width and the height of that bar. All right, so how do we find the width? Well, the width is easy. 500 minus 250. This is a bar of width 250. So width, no problem. And the height, how do we get the height? Well, we can just read it off of this chart. What's the height? It's a little bit more than 0.14. I'm going to call it 0.15. All right, so 250 times 0.15. And that makes a percentage. 37.5% of the trips are between 250 to 500 seconds. Well, of these under 30-minute trips. Okay, so if you want that as a fraction, it's 0.375. Great. So we can see it's very common to have these short trips. Is there a way to find the exact height? You could. If I wanted the exact number, I could also do this with a where clause. Let's see. Probably a better way, if I wanted to know the exact value, would be to do duration where, select all those where the duration is between 250 to 500, and then count how many rows there are in that. And it's going to take a little while to compute because it's such a huge data set, and it tells us there were 129,000 such trips. And then we could look at out of how many, and we could convert that into a fraction. Oh man, where did my, here we go. And as a fraction, get 0.3815. So that's exactly the number. And let's compare to what I got here by looking at the area of the histogram. I got about 0.375. Why were those two numbers different? is because I was estimating the height of that bar visually by just guessing about where it was, and my guess was not exactly right, but it was pretty darn close. Okay. I could also use a bins table and then create a bins table, bin it using the .bin operation, and then that would give me a row that tells me the exact value for the number of items in that bin, in that bar, and then that would be another way to get the exact number. Would I convert that number to a percentage? This number is a fraction, so I would convert it to a percentage if I wanted a percentage. So first, if I wanted a percentage, then I might do like this. And as a percentage, it's 38.15%. Okay, good. All right, let's see. I'm not going to show you how to make a bin table. I showed you that in a previous lecture, but actually, if you don't remember, it's okay. You can reconstruct how to do it with this .where operation. So I'm not looking for you to memorize how to do stuff like how to create a bin table. You don't need to memorize that. Just know some of the basic operations, how to put them together. And then this where clause will let you find all the ones, and you should be able to figure out how to do it on your own. So if you forget, you can reconstruct how to do it yourself. All right, let me remind myself again what we got in this table. Yeah, okay, good. All right, maybe another question I might want to know is, where do people travel from? Like, for instance, what's the most common place to start from? So I could do that by grouping by the start station. And let's just look at the prevalence of where people tend to check out bikes from. That might be really useful if you're running the service, because it gives you an idea. It's not perfect, but it's maybe a start at where the most popular locations are. And so that might give you some ideas for, be a starting point for figuring out allocation for how many bikes to assign to each location. So I'm going to group them by start station and then show counts of how many trips there are starting at each of the start stations. And my computer's plugging away doing that for me. It could take a while because there's a lot of data, and there it did it for me. And you can see the most popular place to start from is San Francisco Caltrain, Townsend at 4th. Okay. Bunch of Caltrain in here, Transbay Terminal. You could also look at a 2D grid where we categorize these these trips according to where they started and where they ended, and look and see how many trips there are between each start and each end position. All right, so computer's gonna work. I love having the computer do its work for me. I can just sit here and hang out. We'll give it a moment. And there's the result. Lots of stuff. And you can see the start station. Each column represents a different start station. Each row represents a different end station. And you could see some numbers. Like there are a lot of trips from 2nd at Folsom to 2nd at Townsend. I suspect those are pretty close to each other, so that's a pretty reasonable. There's also some zeros in there. That's kind of interesting too. Some zeros. Anyone have any idea why there's like a zero right here, for instance, there are no trips between 2nd at Folsom to Adobe at Almaden? Super far, yeah. Different cities. 2nd at Folsom, where's that in? That's in San Francisco. Almaden, that's in San Jose. We're only looking at trips that are shorter than 30 minutes, first of all. So man, you would have to have some like jet power, propulsion or something to get from San Francisco to San Jose in less than 30 minutes. And who's going to do that? That's kind of not the intended purpose of this service. So no surprise that we don't have people who are biking from San Francisco to San Jose. All right. We could now look at maybe the shortest trips. Maybe that's interesting to look at. All right, so we could group this by start station and end station, and look at the quickest trip from each start to each end. So that tells you how fast was the fastest person in getting from one place to another. And we're going to see kind of how quick you can get there if you use a bicycle. So maybe this would be useful if you wanted to get a feeling for about how far apart these stations are if you don't dawdle. Now, this could be a little bit biased. There could be some of these trips could be like, Lance Armstrong or like, some super duper, biking expert who is just racing. But okay, we'll just accept that as one of the limitations of this query. And you could see here, for instance, shortest trips. Well, someone checked out bicycle at 2nd and Folsom and then returned it there. 61-second trip. I don't know what that is. I wouldn't be surprised if that one just checked it out and was like, oh man, no, I changed my mind. I don't need this after all. And you could see here, there was a 60-second trip. I don't know how far apart those are, but you have to be really booking, I think, to be able to check out a bike all the way there and check it back in 61 seconds. All right, so yeah, I forgot something at home. Maybe the bike didn't work. Oh yeah, what's the code? So let me show you the code. Okay, so how to get this? What I did was I grouped by start station and end station, which means I want to cluster together all the rows. All the rows that have the same start station and the same end station should go together, group together. So this is grouping by 2 columns. And then the aggregation operation I used was, instead of counting how many trips there were, I used the min. So I used the shortest duration trip. And then if I'd left out this relabeled operation, then it would, this last column would have been called duration min. But I liked it better as minimum duration, so I just relabeled it just to make it look pretty. Why did I choose to do group and not pivot? Well, son of a gun, I totally could have done pivot. That's a good point. Absolutely no reason whatsoever. Let's try it with pivot. Why not? We can. We'll see if I get the syntax right on the first try or how many tries it takes me. I like that question. All right, so what am I going to do? I want to do an aggregation operation. I don't want counts. So I got to tell it what operation I want to do and what column I want to do that operation on. So what I want to do is I want to do the minimum, not the count, and the minimum of what? The minimum of the duration. So I tell it, well, get your values from the duration column, and the operation I want to do is min. And then I think that might work. All right, so let's do that. It'll take a while for the computer to crunch it all because there's a lot of data. But I love that question. That's also a perfectly reasonable way to do. And boy, I sure hope I didn't have any typo or error in how I typed that, because if I did, it's going to take 5 minutes to go crunch the data and then tell me something's wrong, and I'll have to change it. And it's like take another 5 minutes. And then after do that, another thing I'm going to do is I'm going to look at there's our pivot table. Yay! So same thing. We got this 2D grid, but now we can show here the duration of the shortest trip rather than the number of trips. So this might give you some sense of geographical proximity. Would it be incorrect if you did not do values equals collect equals? Well, if you didn't do values equals collect equals, we in fact did that already. I will show you what you'll get. We did that pivot without a values equals collect equals. It'll give us a table that has the same columns and has the same rows, but the numbers have a different meaning. The numbers are counts of the number of trips rather than the minimum duration. So would it be correct? Well, it's not correct or incorrect. It's just a matter of it would give you different information. Okay. And here, for instance, we have, if you only cared about trips starting at Civic Center, BART, 7th at Market, where can you get to and how long will it take? Well, we can get that from this groups table and then do a where. And you can see how far away other places are. You can get to Powell Street in 97 seconds if you really book it. You can get to Market at 10th in 104 seconds if you're fast. All right. Could I show the code? Let's see. I'll scroll a little to the right. Sorry about that. So what's going on here is I'm doing a where clause to get only starting with, let me scroll back up. Starting with this table here that was obtained by the grouping operation, which has for each start and each end station the length of the shortest trip between those two. And I'm going to filter that down to only the rows that represent trips that started at Civic Center, BART, 7th at Market. And then I'm going to sort them by the duration. All right, looks like I'm out of time. I wanted to tell you a little about how to do mapping data. Maybe we'll tell you that next lecture. Maybe you can look at it on your own. I hope this gave you a sense for how you could take all these techniques we've been showing you and apply them to real data sets and use them to get a feeling for what's in the data and answer some basic questions that you might have. You could go a lot deeper with all this, but hopefully this gave you a little bit of a taste for why we've been teaching you all this and the kinds of things we've been building towards. Go to lab, work on project 1, turn in your checkpoint by Friday. Hope you're working on homework 4 that's due on Saturday, and I will see you in lecture on Friday. Have a good one. Bye.